This is the 55th session on relative velocity. So in this I'll take up a question on relative velocity problem for riverman problem, in which the flow velocity of river is not uniform everywhere. That is, different water particles in general do not have the same flow velocity. Okay. Before this, whatever question we discussed in the chapter on relative velocity for swimmer river problem, man river problem, it was assumed that the flow velocity of river was same throughout. All the water particles were having the same velocity, that it was assumed. Okay. Now in this question we relax this restriction. Okay. In general, we'll take up a riverman problem in which the flow velocity of river varies in general from location to location. Alright. First, what I'll do, I'll write down the question. So I'll write down the question. Okay. A straight river of width L flows towards east. The flow velocity of river particle is not same everywhere. Is not same everywhere and depends on distance y from the south bank as VRG, meaning this VRG is the velocity of flow velocity of river particle, not the velocity of river. Okay. This is given to be 2uy into L minus y by L square, where y varies from 0 to L and u is a positive constant. Again, I would like to repeat this. VRG doesn't mean the velocity of river with respect to ground, but it means the velocity of river particle at a distance y from the south bank. Okay. So VRG meaning has been clearly specified. Alright. S is a swimmer whose swimming speed with respect to river particle in contact, whose swimming speed with respect to river particle in contact is u. The swimmer is initially at a point on south bank taken to be the origin, and swims across the river to a point on north bank, and heading of swimmer is towards north. Okay, fine. This I'll rub it. Okay. Now, taking the coordinate system as specified just now in the diagram, you have to find three things. Taking positive x-axis to be along eastward direction, along eastward direction, and positive y-axis along northern direction. Find first the Cartesian equation of trajectory of swimmer with respect to ground. Equation of trajectory of swimmer with respect to ground. Second, time taken by swimmer to cross the river. Time taken by the swimmer to cross the river. Time taken by the swimmer to cross the river. I'll wrap this, okay? And third, we have to find the drift of the swimmer while crossing the river. The drift of the swimmer while crossing the river. The drift of the swimmer while crossing the river. Alright. So now this I'll wrap everything, okay? So I'll draw the diagram, okay? So this is a solution. I'll draw the top view of the diagram, top view of the river, okay? This is the river, top view. This is the south bank, this is the north bank. The river flows towards east with respect to ground. Width of the river is given to be L. This swimmer is initially at a point on the south bank taken to be the origin of coordinate system. Positive x-axis is along eastward direction. Positive y-axis is along northern direction. Okay. Now in this case the flow velocity of river is not same everywhere. It changes from location to location. It depends on y. So because flow velocity of river is changing from point location to location, therefore the trajectory of swimmer will not be a straight line but some curved path whose equation we have to determine in Cartesian form. So the swimmer moves along some arbitrary curved path like this. Swimmer was initially somewhere here on the south bank initially. At some instant t, swimmer is somewhere here, S bracket t. S for swimmer, t for time. Velocity of swimmer is v, tangent to the path. And coordinates of swimmer at time t are x, y. X component of velocity is vx. And y component of velocity is what? Vy. This vx, vy. And v is the velocity of swimmer with respect to ground, this one. Okay. Now, what we have to do, we have to determine the Cartesian equation of trajectory of swimmer. That is the relationship between x and y has to be determined. Okay. We have to determine the relation between x and y. relation between x and y has to be determined. Okay, fine. So now what we do, the swimmer is here somewhere. Let R be the river particle in contact with the swimmer at this location. R doesn't mean river particle in contact with the swimmer at time t. Okay, so velocity of swimmer with respect to river in ground frame. Velocity of swimmer with respect to river particle R in ground frame at time t is equal to Vsg minus Vrg. What does this Vrg mean? Vrg means velocity of river particle in contact with swimmer with respect to ground. Okay, and this is the velocity of swimmer with respect to ground. See, I'd like to say one thing. Here river is not a reference frame. Because reference frame is what? It is a rigid body of infinite size. What is a rigid body? Rigid body is a body in which collection between any 2 points is constant. In this case, different locations of the river particle do not have the same velocity. So, two locations of river particle do not, the separation between two arbitrary particles of river is in general not the constant. So, it's not a rigid body. If it's not a rigid body, it cannot be a reference frame. Okay, so that's why we are not writing in usual translating frame ways. Vsg equal Vsr plus Vrg, that we cannot say, because river is no longer a reference frame here. So we have to talk in terms of relative velocity between 2 points, as we did here. Okay, so this Vrg means what I have explained it. Fine. Now this Vsr, that this is the heading of swimmer with respect to river particle, it is in northern direction. So this is equal to uj hat. This Vsg is nothing but vector v itself. And this Vrg is the velocity of river particle in contact with swimmer at time t, whose y coordinate is y. That is, distance from south bank is equal to y. So Vrg will written as 2uy into L minus y by L square into I hat. Okay, fine. So vector v is equal to 2uy by L square L minus y into I hat plus uj hat. Okay, now v I'll write as what? Vx I hat plus Vy j hat, that is equal to 2uy by L square into L minus y into I hat plus uj hat. Now we get the corresponding coefficients of I hat and j hat on both sides. If we get the y coefficient on both sides, coefficient of j hat, then Vy, which is simply dy by dt, that is just equal to u. And if we equate the x component I hat, coefficient of I hat on both sides, then Vx is equal to 2uy by L square into L minus y. Okay, fine. So this Vx will let us what? Dx by dt. Alright. Now we have to find the relation between x and y. That is the Cartesian equation of trajectory of swimmer. So from this equation it is seen that dt is just equal to dy by u, and from this equation it is seen that dt is just equal to how much? Dt is just equal to L square dx by 2uy into L minus y. So this is dt, so these two are same. From now in this equation u and u will cancel out, so it becomes 2y L minus y dy L square dx. Alright, 2y into L minus y dy. So this becomes 2yl dy minus 2y square dy is equal to L square dx. Now what we do? Integrate this equation on both sides. Initially the swimmer was at origin, so x coordinate is 0 initially, y coordinate is also 0 initially. At arbitrary instant x coordinate of swimmer becomes x, y coordinate becomes y, this also becomes y. Now 2y dy, L is constant, L goes outside. 2y dy when integrated and inserting limits we get ly square minus this we integrate and insert limits 2y cube by 3. This is just equal to x L square x. So this means x is equal to y square y. So x becomes equal to how much? So I'll write here. Okay, fine. Now I'll rub this. Okay, fine. So from this, if we divide by L square, we get the Cartesian equation of trajectory of swimmer. X is just equal to y square by L minus 2y cube by 3l square. Okay, 2y cube by 3l square, that is the value of x. This is the first equation. This is the answer to the first part of the question. This is the Cartesian equation of trajectory with respect to ground. Okay, so it's not a straight line, it's some arbitrary curve. Okay, it's an algebraic curve. The second thing we have been asked to find out the time taken by swimmer to cross the river. So from this equation we see this vy equal dy by dt, which we wrote here just now. dy by dt is equal to u. dy is equal to u dt. So integral dy is equal to integral over u dt, 0 to t. Capital T is the time taken by swimmer to cross the river. Initially at time 0 swimmer was at origin, so y coordinate is 0. And when the swimmer crosses the river and comes somewhere here, his y coordinate will just be equal to width of the river, L. It is just equal to L. On integrating this and inserting limits, L equal to u is constant. U goes outside the integral, ut. So this means t is equal to L by u. This is therefore the required answer. Fine. So capital T becomes L by u. This is the time taken by swimmer to cross the river. Fine. I'll rub this, okay? Third part is we have to find the drift of the swimmer while crossing the river. Drift. The drift means what? Swimmer is somewhere initially here. When he crosses the river and comes here, then along the river he has moved a distance this much d. This is the drift of the swimmer. So when the swimmer comes here, his x coordinate is just equal to drift d of the swimmer and y coordinate is just equal to L. Okay. Now to find this value of d. So in this when swimmer comes here, d comma L lies on this trajectory. D comma L will satisfy the equation of this trajectory. So x is equal to y square by L minus 2y cube by 3l square. Swimmer comes here, the d comma L, this point lies on the trajectory of swimmer. So this point will, coordinate of this point will satisfy this equation. So for x we write d and y we write L. So d is equal to L square by L minus 2l cube by 3l square. This becomes L minus, this becomes L minus 2L by 3, that is just equal to L by 3, which is therefore the required answer. Fine, alright. So this problem I demonstrated how to deal with questions in which flow velocity of river is not uniform but varies from location to location. I hope it is clear. Alright, fine, alright. This is a bit now, fine. In this session, I'll take up one more question, okay, on relative velocity for translating frames. Question is this. The barrel of a tank moving leftward with respect to ground at a constant speed u makes an acute angle alpha with rightward horizontal. with rightward horizontal. This tank fires a shell with a muzzle velocity of 3u. Find the value of alpha so that horizontal range of shell is maximum. Horizontal range of shell is maximum. Okay, fine. So this is the question. Now what we'll do, first we'll identify the frames under consideration. Instead of object under consideration is shell, S, denoted by what, say, S, say. Instead of frame and we have the tank frame, tank, denoted by T, say. Instead of F frame we have the ground frame, denoted by G, say. Alright. Instead of shell we have S, instead of tank we have T, instead of ground we have G. Alright, fine. Now what I do, I draw the diagram of the situation. This is the tank. This is the tank, alright. This is the barrel. This alpha. Tank is going leftward at a constant speed u with respect to ground. This barrel makes a constant angle alpha with rightward horizontal. This barrel fires a shell at a muzzle velocity u, 3u. So what does muzzle velocity mean? Velocity of the shell with respect to tank just after it emerges from the barrel. That is the muzzle velocity. That is called the muzzle velocity, 3u. Velocity of shell with respect to tank just as it emerges from the barrel. Okay, that is called the muzzle velocity. So 3u is the muzzle velocity of shell with respect to ground. Okay, 3u is the muzzle velocity of shell with respect to ground, and u is the velocity of tank with respect to ground constant. Okay, now what we do, we take this rightward direction to the x-axis, upward direction to the y-axis. So when the shell emerges from here, okay, it will have some velocity with respect to ground, say Vsg. So Vsg will be written as velocity of shell with respect to tank plus velocity of tank with respect to ground. Fine, alright. Now velocity of shell with respect to tank is just the muzzle velocity 3u. So this will be written as 3u, and I'll not write 3u, sorry. Velocity of shell with respect to ground is that is 3u, that is along this direction, and so it will be written as which will result in x and y. It will be 3u cos alpha I hat, 3u sin alpha j hat, okay, plus velocity of tank with respect to ground, which is u in negative x-axis, u into minus I hat. Alright, fine. So I'll rub this one, okay. So this Vsg are denoted by V, say. So V will be written as Vx I hat plus Vy j hat. Okay. So this becomes 3u cos alpha minus u into I hat, 3u sin alpha into j hat. Alright. Now, so x component of velocity of shell with respect to ground is how much? Vx. That is equal to 3 cos alpha minus u, and y component becomes how much? 3u sin alpha. Okay. Now see, from one thing we must note. Velocity of shell with respect to ground will have some direction in this way, say. Vectors of these two. 3u this way, u this way. Resultant will be something like this. So I'll just draw a portion of it here. like this. Barrel, this is the barrel. Shell will come something like this. Outside with respect to ground, VSG will be something like this, which is just V. Is it clear? Because VSG, the V is the vector sum of these two, VST and VTG. VST is along this direction and VTG is along this direction. Resultant will be something like this. This is V, theta angle. Okay. Now we know from the theory of projectile motion, whose many videos have been uploaded in this entire. If you go to the previous videos, you will get so many questions on projectile motion. It is well known that range R of projectile motion is given as V squared sine 2 theta by G, where V is the speed of projection. That is same as V square into 2 sine theta cos theta by G. Alright. That is same as 2 times V cos theta into V sine theta upon G. That is same as 2 Vx Vy upon G. This is the horizontal range of the projectile, of the shell, with respect to ground. 2 Vx Vy by G. If Vx is what? Vx is this much, Vy is this much. Alright, fine. Now I love this one, okay? So Vx Vy substitute in this. Therefore, our horizontal range of shell R is 2 times Vx is simply 3u cos alpha minus u into Vy is simply 3u sin alpha by G. This becomes 3u square by G into 6 sin alpha cos alpha minus 3 sin alpha. This becomes 6 sin alpha becomes 3 sin 2 alpha minus 3 sin alpha. This is range. Now we have to find the value of alpha so that R is maximum. So when R is maximum implies from the rule of calculus, maximum in your theory, dr by d alpha is 1 is 0. So derivate this equation. 3u square by G comes outside the differentiation. Only this term remains. When differentiating this with respect to alpha, this becomes 6 cos 2 alpha minus 3 cos alpha is equal to 0. So this becomes 6 cos 2 alpha is equal to 3 cos alpha. So 2 cos 2 alpha is equal to cos alpha. Is it alright? Fine. Fine, alright. So this will be 2. This will not be 3. This will be calculation mistake it was. Is it alright? Fine. 3u square by G common. So 3 into sin 2 alpha minus. Okay, fine. This is alright. Now this we have to solve. That's all. This I will rub it. Okay. So now cos 2 alpha is written as 2 cos square alpha minus 1 from trigonometry. 3 becomes 2 cos square alpha minus 1 minus 2 cos alpha is 0. Fine. So this becomes cos alpha minus 2 cos alpha minus 3 is 0. Alright. So cos alpha from theory this becomes 2 plus minus root under 4 plus 72 by 12. So this becomes, is alright, fine, here 4 to 12, 72, okay, that's correct. So this becomes 2 plus, since alpha is acute, so cos alpha is positive, so negative root is rejected. So therefore we get 2 plus root 76 that is simply 2 root 19 by 12. So this becomes 1 plus root 19 by 6. Okay. This is alpha, cos alpha. So alpha becomes cos inverse 1 plus root 19 by 6. This is therefore the required answer. So if alpha is taken to be this much, then horizontal range R of the shell with respect to ground will be maximum. Alright, fine. Cos inverse 1 plus root 19 by 6. Cos inverse 1 plus root 19 by 6 is therefore the required answer. Is it alright? Fine. So therefore, fine. So this I'll close it just now. In next session also I'll take up some more problems on relative velocity problems. Okay. Also I'll close it here.